Welcome back. I have a problem here. I have this blue container. The force of gravity of this blue container is 500 G. Then we also assume that the mass of this blue container is much greater than the mass of this beam here. So we neglect the mass of this beam. Therefore, we say that the mass of this blue container is 500 kilograms. Also, you have symmetry here, 2 meters to the left and 2 meters to the right. So your cables here, they connect this beam with this blue container. And then you also have 2 cables here that is connected to this ellipse. And then you have a force that holds this entire structure in place. So this entire structure is not accelerating anywhere. And now my question is this. You can see that due to symmetry, the length of these 2 cables are the same. And we also know that the maximum tensile force in those cables is 3.5 kilonewtons. So this cable can withstand 3.5 kilonewtons and this one as well. And now my question to you is, how does the tensile force in these cables depend on the length of these cables? Meaning that if instead of this configuration, I had this configuration instead, where my length is obviously smaller, will this increase or decrease the tensile forces in the cables? Similarly, if I have this kind of situation, and this is my ring, then now I have more length in my cables. So will that increase or decrease the tensile forces in the cables? So the first question is, how does the tensile force depend on the length? No specific mathematical formula is needed. I just want you to tell me that concept-wise. If the length goes up, will the tensile force go up or down? And if the length goes down, will the tensile force go up or down? And then once you have figured that out, the second question is, what is the minimum or maximum length of these 2 cables? When is the border? At which point the cables will break, considering this information here? So try it out by yourself first, and then let's do it in the next video. Thank you very much. Welcome back. So let's now solve this exercise. Let's find out how the tensile forces depend on the length of the cable here and here, and what is the breaking point of these cables. First of all, let's analyze this structure a bit more. So this is my blue container that I'm gonna draw here. You have a force of 500 G that points down, but since this blue container is not accelerating anywhere, that means that these 2 cables, they hold this blue container in place. Now normally, you would have to calculate these forces. Let's say that if the mass of this container is not uniformly distributed, so you have higher mass density here and lower mass density here, then your force of gravity would be somewhere here. And then you would have to calculate these 2 forces, which would be different. In this case, this one would be bigger than this one. But we'll get to that in the future sections. This would be a rigid body equilibrium problem. However, in our case, it's different. We assume uniform mass, so the center of gravity is in the middle, and so you have symmetry here, which tells you that this force of gravity here is counteracted by these 2 forces here, and they are equal to each other, meaning that this would be 250 Gs, and this would be 250 Gs. There is no reason why they would be different, because you have symmetry here. And then, due to Newton's third law, these are your 2 cables here, this is the beam, again, due to Newton's third law, you have the same forces here that are opposite to each other. And then here, you would have two unknown forces. You have these two cables here, these ones here. You have the same forces here, and then also here. And then you have this ellipse here, and you have the same forces in this direction. And then you have your F here. So let's call this point B and this point C. And remember this one here, it's A. So that means that you have a force here, FAB, and here, FAC, and the same thing here and here. And due to symmetry, you can also right away see that FAB equals FAC. And now, first of all, I want to ask you, what do you think what this force F is? You can find it without any calculations. All you have to do is to imagine this entire structure as one object. And so if you have force of gravity equals 500 G in this direction down, then that means that since you have total symmetry here, this force here is also 500 G, but it points up. So F equals 500 G. You can also see it from the equilibrium principle. The sum of the forces in the y direction must equal 0, and so you have F minus 500 G equals 0, which means that F equals 500 G newtons. What about this FAB and FAC? Well, if we assume that there is some kind of angle here, let's call it theta, and due to symmetry, we also know that you have the same angle here, theta, then if we only focus on this beam here, and we perform equilibrium principle only on this beam, then we will have FAB times cosine theta minus FAC times cosine theta equals 0. So from here you already see that FAB and FAC, they are equal to each other. And then if we apply this principle in the y direction, then we will have FAB times sine theta plus FAC times sine theta minus, and then you have 2 times 250 G, because you have two forces that are 250 G here, and that will give you 0. So you can say that FAB times 2, because remember, FAB and FAC, they are the same, so I could just write FAB times 2 times sine theta, and that will give you 500 G. Then we can say that FAB equals 500 G over 2 times sine theta. Now remember that your FAB and FAC, these are your tensile forces that you're looking for. And now you can already answer the first question. Right now, your FAB is written as a function of theta. And in general, we can just say that this is our tensile force. So FAB equals FAC equals the tensile force in these cables. Right now, we have T as a function of theta, and you have sine theta in the denominator. Now, when theta increases, if theta goes up, then logically, your length goes up. So what happens when theta goes up? Well, our theta can range here, let's say, from 0 till 90 degrees. So this is your sine function. This is 0 degrees here. This is 90 degrees. So if theta goes up, then also your sine function will go up. It becomes bigger. But it's in the denominator, which means that if your denominator becomes bigger, then your tension force becomes smaller. So if your length increases, then your theta increases, then your sine theta increases, and then your tensile force decreases, which means that increasing the length of these cables decreases the tensile force here. However, if your length decreases, it becomes something like this, then obviously your thetas are smaller here. And as a result, your sine theta goes down. So your denominator becomes smaller. That means that your tension force becomes greater. So decreasing the length of these cables increases the tension force inside those cables. And you can see it thanks to this equation. And now, since we know that decreasing length increases the tension force, we know that we have to find the minimum length. So if the cable is less than this L min, then the cable will break because the tensile forces will be too great here. We can have this situation where the length is greater than L min because then your tension force will be smaller, but in this case, your tension force will be greater and your cables might break. And so your L min happens at this force here, 3.5 kilonewtons, or in other words, T max equals 3,500 newtons. And so in order to find this L min, we take this equation that we have here, and we say that it equals to T max, or FAB max, meaning that this expression equals 3,500 newtons. That's our equation. If we rearrange it, then I will have this expression here. I have 250 here because I have 500 over 2, and so I can just get rid of this one and say that this 500 becomes 250. And so from that, you know that theta equals inverse sine this ratio, which means that theta equals 44.5 degrees. Here you need to make sure that you always round up, because if you have a very long number here, and you obviously need to round your numbers, then since this is such a critical angle, meaning that if you go a little bit down, then your cables might break, then even if normally you would round this angle down, let's say that you have 44.44 degrees, then normally you would say that, okay, it's 44.4 degrees, but then your cable might already break. So in this case, better say that it's 44.5 degrees, just to be safer. And so now, since you know that your theta equals this one, and also this one, then you can calculate the length of these two cables. If I say that this angle here is alpha, and I know that this side of the triangle is 4 meters, 2 plus 2, then I can say that alpha equals 180 minus 2 times 44.5 degrees, that's 91 degrees, and then since this side is 4 meters, I can use the sine law. I can say that 4 over sine 91 degrees equals, and then I take one of the sides, L, and in this case it's L minimum, because this theta here, it's also theta minimum, and then I write here sine 44.5 degrees, and that will give me this expression, which is 2.81 meters. Again, this is not an exact number, but make sure that you round it up just to be safe. And there you go, that's how you find your L min. If your length in the cable is below this length, then your cable will break. If it's above this length, then you're fine. So now you see how your tension forces in the cables depend on the length of the cables. Thank you very much. Welcome back. I have a device here that is used to straighten the frames of wrecked cars. And so what I have here is a hydraulic cylinder that applies force in this direction, and it's 3,500 newtons. And so the cables here are like this, as shown. And so what we need to find is the following. We need to find the tensile force in this part of the cable and in this part of the cable. And you have all the necessary dimensions. And so try this exercise by yourself first, and then I'll show you the solutions in the next video. Thank you very much. Welcome back. So let's now find these two tensile forces. For that, we take this point B as our particle. So we start with our free body diagram. This is our coordinate frame. And so this is B here. And you have a force from this hydraulic actuator. It's in this direction. And then you have this force, TAB, and this force, which is TBC. So I need an angle here. Let's call it alpha. And here, let's call it beta. We can find these angles using these dimensions. For example, this alpha here, essentially is the same one that you have here. And this beta here, it's essentially this one here. And so you can clearly see that tangent alpha equals 450 over 400. You take the opposite side divided by the adjacent side. From that, you know that alpha equals inverse tangent 450 over 400, 48.4 degrees. That's your alpha. Then tangent beta equals 450 over 250. Again, the opposite side divided by the adjacent side. That gives you inverse tangent 450 over 250 and 60.9 degrees. That's your beta. And now you just apply the equilibrium principles. In the x direction you have minus TAB plus TBC times cosine beta plus 3,500 times cosine alpha. And that must be 0. And then in the y direction, you have minus TBC times sine beta plus 3,500 times sine alpha. And that gives you 0. So let's first take this equation, the second one. TBC times sine beta, that's 3,500 times sine alpha. TBC, that's 3,500 times sine alpha over sine beta. You already know these values. And so that will give you 2,995 newtons. And then you take the first equation and you simply take this one and you put it onto the other side of the equation sign. So you will have TAB equals, and then all this, you know your TBC, you know your beta, you know your alpha, and so your TAB will be 3781 newtons. And since they are all positive, it means that our assumptions about their directions were correct. And that's it. Thank you very much. Welcome back. I have two springs here, and right now they are neither stretched nor compressed. And then you have two rings here. You have 2 meters here, 1 meter here, and 2 meters here. So these are the horizontal distances. And this is the vertical distance, 1.5 meters. So let this place be A, this one B, this one C, and this one D. And then what I will do is the following. I'm going to place two cylinders here that have masses MA and MB. If I do that, then these two rings connected by this cable, together with these cylinders, they will go down, meaning that these two springs, they will be stretched. And then vertically, these rings will go down by 0.5 meters. So first of all, let's talk very quickly about springs. Springs, unlike cables, can also be compressed. Let's say that you have an unloaded spring here. Its length is L0. Now I apply force in this direction. And we of course assume that this spring is connected to some kind of wall. And so in this case, the spring will elongate and the additional length is plus S meters. And then you can calculate this force with this formula, F equals K times S. Now remember, you apply this force to the spring, and so according to the Newton's third law, the spring applies a force that is equal in magnitude and opposite in direction to you. So if you look at this ring B, let's have it here, then this spring here applies a force in this direction to this ring. Just like from the spring's point of view, the force is in this direction here. And then of course, you have a force with the same magnitude here, and then also here, and this is this point D that you have here. So the Newton's third law still holds. And so if we look at this formula here, then this S, that's the additional length in spring that occurred because of this force. So if this is the total length, then S equals L minus L0. So the unit of S is also meters. Since we have a tension force, by convention, S is positive, which makes sense because if this is 4 and this is 5, then 5 minus 4, well, that's positive 1. And then this K here, it's the spring constant, and its value depends on the spring. Different springs have different Ks. Mathematically, it's simply a proportionality constant. So let's say that I have two axes here. Here I have S in meters, which is this one here. And then here I have force in newtons, which is this one here. And essentially, if you look at this formula, then it looks like Y equals A times X. Y is like force, and then X is like S. And then this A, that's this K. Essentially, it's a slope. So if I have this straight line function, and I say that this here is delta F, and this one is delta S, then K, it's simply the slope of this straight line. And you can also see that the units of K are newtons over meter, which makes sense because here you have meters and here you have newtons. And if you multiply K by S, then you multiply Newton over meter times meter, the meters cancel out, and you have newtons, which is the unit of force. Now, just to mention that in this course, we will be using this formula. This formula is a good enough approximation for as long as the spring does not experience too much tension. Of course, if you apply too much force, then your spring will not return to its original position. Essentially, you will have ruined the spring. And then, of course, then this formula is not valid anymore. And another way to look at this K is that it essentially tells you the strength of your spring. You can imagine that for this K here, if you create so much S, then your force will be like this. But let's say that you have another spring that has a higher K value, which means that the slope is greater. In that case, for this S value, you have to apply more force. In other words, if you apply the same amount of force, then you will get less S. Or, for example, if you choose a spring that has a smaller K value, then your slope is smaller, and for the same amount of S, you have to apply less force. In other words, if you apply the same amount of force, then you will get more elongation. So that's the meaning of this K value, which is the spring constant. And finally, if I have an uncompressed spring and I apply force in the compression direction, then obviously your spring gets compressed, and this becomes L. And then you have minus S. And it makes sense because L minus L0 equals S. So if this is 3 and this is 4, then 3 minus 4 equals minus 1 meter. Now, of course, when you apply force like this, then because of the Newton's third law, the spring applies a force to you that is equal in magnitude and opposite in direction. And so in general, this law, F equals K times S, it's called the Hooke's law. And of course, if your S is negative, then your force becomes negative. And that's the convention that we need to remember. If this is your spring, and the spring elongates, then it's in tension. Thus, S and F, they are positive. However, if you apply a force to the spring, and the spring gets compressed, and it's in compression, then your S and your force magnitude are both negative. And now, if we look at this problem here, then both springs have a spring constant K equals 100 Newton over meters. So this one and also this one here, both of them are K equals 100 Newton over meters. And so in this white case, when you don't have these cylinders, that's when your springs are not elongated. They are in their natural states. It means that in this case, S equals 0 meters. And now, knowing all this information about springs and knowing these dimensions, your task is to calculate the masses of these two cylinders. So what is MA and what is MB? So try it out by yourself first and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this problem and find mass A and mass B. Now before we make any kind of calculations, let's see if there are some obvious simplifications due to symmetry. You can clearly see that from this middle line here till this point here, which is point D, and this point here, which is point C, on both sides you have 2.5 meters. Now this in itself is not enough. Let's say if this K here was bigger, I don't know, maybe 200 newtons over meter. So instead of 100, we have 200 newtons over meter. And here we still have 100 newtons over meter. That means that in order to achieve this situation where these cylinders are on the same horizontal level, MA should be greater than MB, because this cylinder needs to be heavier because you need more of force of gravity to elongate this spring, because it has a higher value for its spring constant. But that's not the case here. Here, both spring constants are equal. They are 100 newtons over meter. And you also have symmetry horizontally, and both of your cylinders are on the same vertical level. For example, they are not something like this, where this blue cylinder is on a lower level compared to the orange cylinder. That's not the case here. Here they are on the same vertical level. And so considering that they are on the same vertical level, and considering this horizontal symmetry and considering the fact that both spring constants are equal, it is reasonable to assume that MA equals MB. Under these assumptions, there simply is no other way. So let's just call both masses M. Let's use this variable. And so let's start with our free body diagram. You have this ring, A. The force of gravity due to this cylinder is mg, and then you have this force, FAC, and then you have this force, FAB, and then you have ring B. Due to Newton's third law, you have the same force here, only in the opposite direction. To be completely correct, it should be BA, but since they are equal, then I will simply write it to be AB. And so you have this force of gravity here, mg. Since the masses here are equal, the force of gravity here is also equal. And so you have another force here, FAD. And again, due to symmetry, you know that FAC and FAD are equal to each other. That's because the spring constants are the same. You have 2.5 meters on both sides from this middle point. Both rings are on the same vertical level. It means that in both cases, you have the same angle. And therefore, from these free body diagrams, you can easily see that FAC must be equal to FAD. Again, that's because the spring constants are the same, and the vertical levels are the same. And also there is symmetry horizontally here. So I'm just going to say that this force equals F, and also this force equals F, since they are the same anyway. And now what I want to do, I want to find the length of this spring when it's unloaded. So this is my L0. And also this spring has L0. Again, because you have symmetry here, 2.5 meters to the right, 2.5 meters to the left. Vertically, they are both 1.5 meters down, and the spring constants are the same. Now, to be more correct, this is the full length of the unloaded spring, and the same thing here. And now it's very easy to find this L0. You can use the Pythagoras theorem. You have 2 meters here, horizontally, and then here you have 1.5 meters. So essentially you see that you have a right triangle here, and this L0, it's your hypotenuse. And so you can say that L0 squared equals 2 squared, 2 is this length here, plus 1.5 squared. 1.5 is this vertical distance here. And if you square root it, then your L0 becomes 2.5 meters. So there you go. This is 2.5 meters, and this is 2.5 meters. And now what I want to do, I want to find the length of this spring, L, in this loaded mode. The springs are loaded when you attach the cylinders here. Again, since the masses of those cylinders are the same, and there is horizontal symmetry, and vertically they are on the same level, they both have the same L. And it's very easy to find it as well, because again, this distance here, it's 2 meters, and now here, this distance, well, it's simply 1.5 plus 0.5 meters. So it's 2 meters here. And of course, this is a right triangle, so L squared equals 2 squared plus 2 squared, and then if you take the square root of it, then it's square root of 8 meters. And now what you can do, you can calculate this S, which is L minus L0. So it's square root of 8 minus 2.5 meters. And that will allow you to calculate this F force here, which is the same one like this one here. So F equals, K times S. So it's 100 times, and this is your S value, so it's 32.8 newtons. And now, because of the fact that I know this F force, I only need to apply the equilibrium principle in the Y direction. And I can choose either of those free body diagrams. So let's say that I choose this one here, B. Remember, this is positive X, this is positive Y, and actually you already see it here. Here I say that positive Y points up. Now what is this theta angle? Well, if you look at this right triangle, then you have 2 meters here and you have 2 meters here. So what's this theta? If this is your right triangle and you have 2 here and you have 2 here, then of course here, already without calculations, you know that it's 45 degrees. So that just comes from geometry. This here is 90 degrees, and because of the fact that all the sides are equal, then the diagonal in this square will give you a theta, which is 45 degrees. And so since you know this angle, you can write F times sine theta minus mg equals 0. And that means that mg equals F times sine theta. In other words, m equals F times sine theta divided by g. So you have 32.8 times sine 45 degrees divided 9.81 meters per second squared. And that will give you 2.36 kilograms. And that's both for MA and MB. So as you can see, when you have symmetry, then you can simplify your calculations by a lot. So always look for some symmetries. However, be very careful when you apply them. Because for example, in this case, since we don't have cables here, we have springs. And here we had to make sure that we were using the same springs. Because you might have geometrical symmetry, but when your spring constants are not the same, then you might get wrong answers. So that's it with this problem. Thank you very much.